Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, we're going to be dealing with extreme precipitation frequency events. In this exercise, we'll use HMS project files, data, and instructions to assess the magnitude and uncertainty of extreme precipitation frequency events routed through HEC HMS. So what I have on the screen here is my HMS. There's nothing there because we need to start by downloading the project files from the website. So go ahead and check the description to this video. The first link will be a link to the files page here, extreme precipitation frequency events. And then right down here is the project files. So go ahead and click this link, extremeprecipfreak.zip, and then wait for that to download. Okay, so that's downloaded for me. There's a zip file off to the side because I just designated my desktop as the default download target directory. Now I have this frequency folder. Okay, so that basically stood for the HMS project folder. What I'm going to do is copy those files into my project directory where I want to keep them. That will unzip the files and make them ready for use. And then once that's complete, I can delete the zip file and I'm ready to go. Now what I'm going to do is navigate to this directory and open up the HMS file from HMS. So let's do that. Open and then browse project. Here it is. And then extreme precip frequency.hms and select. All right. So what we have in our project is a lot of things. We have a couple basin models. So I'm just going to load those up onto the screen. Tule River and Tule River no snow. We just keep one of those up there for visual. Okay. It's a little overwhelming, some of these layers, so I'm just going to toggle off the terrain and the discretization. Okay, that looks a little bit more easy to deal with. Also, in the Watershed Explorer, I'm just taking a quick tour to look at the files we have to start with here. We have a meteorologic model. There's a control specification, some time series data, some paired data, some grid data, and a terrain data. In this exercise, we're going to investigate the exceedance probability of a dam overtopping, which is going to be at a reservoir in this downstream most hydrologic element of our model. This is technically a junction, but it's going to serve as a reservoir so we can measure the peak inflow during our 3 different simulations. Those simulations will be the 1 in 1,000 annual exceedance probability event for a 24-hour duration storm, as well as a 1 in 5,000 year and 1 in 10,000 year. So the 1 in 1,000 year data is going to come from NOAA Atlas 14 data, and then the 1 in 5,000 and 10,000 year trials 2 and 3, that would be from some other data, which we'll get into as we get going here. Occasionally in this exercise, I'll bring up the instructions. Again, this is the tutorial. We have our introduction. Step 1 is to open HMS. Also, it says to take a quick look at the reservoir inventory, which is up in the parameters menu, element inventory. And now we have our reservoir inflow. This is the junction that is at the bottom of the subbasin. And you can see that the drainage area here is about 390 miles squared. If we scroll down, we're on to step 2 here. So during this exercise, I'll be referring to the steps as step 1, step 2, and so on. Just go ahead and reference this tutorial page if you're lost. Import the precipitation frequency data. To do that, we're going to click on this link down here for the NOAA National Weather Service Precipitation Frequency Data Server. And then this is what it comes up to. Go ahead and click on the California location because that will be the location for this exercise. And then after that, at the top of the page, we want to switch this partial duration to annual maximum, which is the only other option to select. Then scroll down a little bit and click on the supplementary information tab in this table right here. It's the 3rd tab over. So go ahead and click that. And then under the second item, PF in GIS format, which is right here, what we want to do is select an annual exceedance probability of 1 in 1,000. And then the duration is going to be 24 hours. Then go ahead and click submit. That's going to download that data in a zip file. All right, we're almost done downloading. Okay, we're done there. Here off to the side, here's my zip file. So I'm going to open that up. I'm going to put the contents of this file into my data directory. And just to kind of keep things organized, because there's technically 3 files here, I'm going to put it into a separate directory that I create. Okay, so here is my project directory. I'm going to go up to the data directory. We already have a lot of data here. So what I'm going to do to just kind of keep things organized, okay, these are all DSS files mostly, a couple TIFFs. I'm going to just create a separate directory so I don't get things lost. And I'm going to name it basically the name of the file, SW 1000 year 24-hour AMS, and then underscore NOAA is what I added to the end just to help me remember that the source is the NOAA Atlas 14 data. All right, so that's copied over. So it's unzipped and ready to go. I can now delete the zip file. Now what I want to do is go back to HMS and create a gridded data set for precipitation frequency for this ASCII file right here. Again, this is the 1000 year data that's for precipitation frequency. To do that, I'll go up to components and then grid data manager. Now for the data type, I want to select precipitation frequency grids. So scroll down a little bit. There it is. New. For the name, I'll just give it the name here. Some of these names are provided in the tutorial itself, so I'm just going to keep with the same naming instructions. Create, and now we can close that. Over here in the Watershed Explorer under the grid data, I should now have a new record under precipitation frequency grids right here. So I'll go ahead and click that. Now I can define what that data is down here in the components editor. I'm going to start by selecting a data source as an ASCII file, and then I'm going to navigate to that ASCII file that we just downloaded. So here is my project directory, here's the data directory, and then here's the directory that I just created to sort of keep these files to themselves. There is the ASCII file, and then we'll go ahead and click select. The next thing I need to do is specify that the units are in inches, and that's already done. And then the scale factor is going to be 1000. The unit scale factor will be 1000 for the Atlas 14 data that just basically divides by 1000. And then for Atlas 2, it'll be 100,000. But if you're using the actual values, you could just use the scale, leave the scale factor at 1, which means there's no change. So I'm going to go ahead and save that. Now we need to basically do the same thing for our 5,000 year grid 24-hour and 10,000 year grid 24-hour. Now we can't use the Atlas 14 data. It only went up to 1,000 year, but the project files that we downloaded actually contain the data that we need. So what we're going to do is go up to the components menu, grid data manager, and then we're going to select the type precipitation frequency grids, just like we did before, and then click new. Okay, the 5,000 year will be named CA 5,000 year, and then the 10,000 year will be named for 10,000 year, and then create. Okay, so we can close the manager. Now we have 2 new records here for 5,000 and 10,000. For our data source, we're going to select a TIFF file, a GeoTIFF, and then navigate to the GeoTIFF file for 5,000 and 10,000 year exceedance probability. Okay, so I click data. It's not a DSS file, it's a TIFF. So what we have here are TIFF files and then this directory. So I have 5,000 year selected right there. So I'll click 5,000 and select. For units, I want inches, and then the unit scale factor will be 1. So the actual data is saved in that TIFF file. Okay, we're going to check out that TIFF file in just a moment, but let's just do the 10,000 year record while we're here. So same thing as before, I'll select GeoTIFF, select the 10,000 year record, and then select inches and 1. That looks good. I'm going to bring up QGIS and just take a look at that data just to get an idea of what we're looking at, how much precipitation is actually falling in a 5,000 year storm and a 10,000 year storm for a 24-hour duration. So I got QGIS up on the screen here. I'm going to go add layer, add raster layer, and then navigate to that TIFF file. Here's the project data, and then here's the TIFF file for 5,000 year. Okay, I'm just going to add it. I'm not going to mess with the settings or anything. So here is the data. Let's go ahead and add the 10,000 year record as well. Layer, add layer, raster layer, and then it should be in the same directory already. Okay, it is good. 10,000 year and add. So that was added over my table of contents panel over to the left here. I see my layers. So for 10,000 years, actually, let's look at 5,000 year first. Okay, I'll just move that there. Okay. So for 5,000, let me inspect the elements. So for instance, let's see, over to the right, I have the attributes showing up. Okay, I resized the screen to make it a little bit easier. What we have here is 6.3, 6.3. A middle number would be 14 inches, 14 inches of rain in 24 hours. That's insane. And then this is probably the highest one, 24.59. So that's huge. I'm going to right click properties and just take a look at the mean. Yeah, so about 14 or closer to 15 inches of precipitation in a single day. That's the 5,000 year average for that grid. Okay. And then 10,000, I would expect to be a little bit higher. So if I inspect, we have 7 kind of on the low end, 21 inches in that day of rain on the high end or middle, and then 27. So if I peek at the statistics real quick, we have a 16.5 inches of precipitation for a single day on the 10,000 year recurrence storm at that location in Central California, I believe. All right, I'm going to go ahead and close QGIS. That was just a little side quest. Okay, we're on to step 3 of the tutorial. It says to import temporal patterns. The tutorials and guide instruction page gives us this link here to download that data. This is another NOAA website. First, what it tells us to do is select the station, and that is by the station name. So this manually select the location. Part B is the station name, lists in California, because that link did a filter for just California, I presume. So we're going to select the station Success Dam Weather Station 72-0036. Now this appears to be alphabetical, so I'm just going to zoom down to the S. Okay, there it is. Success Dam Weather Station 7236. So that's good. Scroll down and click on the Supplementary Information tab again, which is here. For part 4, temporal distribution, change the duration to 24 hours. So that's right here. It's already 24 hours. This is the data I want, the temporal distributions. So go ahead and click Submit, and then wait for that to download. That was quick. That was a small file, so it's downloaded. While we're here, let me just take a quick peek. This is a CSV file, so it should open up in a text editor, but might be a little hard to read. Here is the data from that CSV file we just downloaded. It is cumulative percentage of total precipitation for the first quartile cases. We have time and then the percent of occurrence. Now there's actually 4 tables here. This is just the first quartile. If we scroll down a little bit, there's the second quartile and so on. These tables show the cumulative precipitation percentages for rainfall events. The first quartile in this case represents events where the precipitation happens early on in the event, and the columns represent the different percentiles right here. So we're going to see this in just a little bit later in a table format, and more importantly, an easy to understand a graph, which shows us the comparison between these different percentages over the course of a 24-hour time. So here's a 0, and then the last hour is 24 hours with a, looks like a 30-minute time step. Okay, I'm going to navigate back to HMS here. And what we want to do to import that data is go Tools, and then Data, and then Atlas 14, Temporal Pattern Importer. Now we want to navigate to that CSV file. And right now it's on my desktop. I forgot to actually put it into my data directory, so I'm going to do that right now. I think I can just put it there. That's fine. It's the only CSV file here, so it shouldn't be hard to find. All right, let's navigate to that data directory, and let's see, make sure I'm in the right spot. Project. Here's the project. Here's the data. Now there should be a CSV file in here somewhere. Okay, there it is right there. And open. All right, I'm going to go ahead and click Next. And I want to include all 4 quartile cases, 1, 2, 3, and 4. Next. Now it's telling me this is the path that it's going to export that data to, or it's going to transport the data from the CSV file into a DSS file, and then it will be read in to HMS via the DSS file paths. And that's fine. Here's the name of my project, the data directory, and then it's just going to create a new .dss file with the name CA region 10 24 hour. Looks good. Next. All right, so it says import complete. Let's go ahead and see what we can find here. I'm going to actually open up DSS View, because why not? Let's check out that data visually using a tool that's made for that exact purpose. Let's go ahead and open, navigate to the project, and then data. Now there's a DSS file that says this one right here, CA region 10 24 hour, and open. Now what we should see is the different data sets from that CSV file. So for instance, we have 24-hour quartile 1, 10%, 24-hour quartile one, 20%. All these are for the 24-hour duration. That's what we downloaded. And then these are the first quartile. Here is the second quartile data, and then third and fourth. So we only have 36 records, it looks like, because there's no 0 or 100% data. Let me just open up the 10% data. All right, so this would actually be more meaningful if I open up all percentages for the same quartile first. There we go. So what we see here in this plot is for the first quartile, where most of the precipitation falls in the first quartile, the first quarter of the storm duration, or at least the most of any quartile. We see the different percentages here. The horizontal axis here would be the percentage of the duration of the storm, and then with the 24-hour period in this case. And then the vertical axis would be the percentage of the precipitation, cumulative precipitation. All right, so what I want to do now is compare the same percentage, but for different quartiles. So let me just stick with 50%. That's what I happen to have selected here. I'm going to hold down Control and select 50% from the second quartile, third quartile, and fourth quartile, and then check out this plot. So this makes sense for the most part. Here's blue. We already saw this one. This is first quartile. Red is second quartile, and that's where the slope is steepest, between 25 and 50%. And then the green here is third quartile. Most of the rain, or the highest rainfall intensity, occurs during the 50% to 75%, and then the fourth quartile. Okay, so now that we've looked at that data, we can close DSS. In the Watershed Explorer, if I go to the paired data directory, I should now have percentage curves right here. So that CSV files, those percentage curves should be loaded up right here. And sure enough, they are. We've got what looks like 36 records. I can also look at the table data and the graphs, but this is just individually. Okay, we're on to step 4 now. That is to enter the area reduction information. Going to Components menu and then Paired Data. Next, we're going to select the type Area Reduction Functions, which is right here. Click New, and then for the name, I'm going to call it HMR 59. That's the name of this report. Sierra 24-hour, and then Create. Okay, we can close that. Now I'll open up my paired data directory, and we should have area reduction functions. I'll expand that. Here's the record we just created. We're actually going to go with manual entry, and then the instructions have a table with the actual data to input, and then just paste in the data directly. This is the data that's provided to us on the instructions, so that's where that came from. And then we can take a look at the plot right here. We're on to step 5 now. This is to create a hypothetical storm meteorologic models. So we need to actually create 3 meteorologic models. Up here in the Components Meteorologic Model Manager, we already have 1 meteorologic model, but we need to create 3 more. So let's get started. Select New. I'm going to create the first one for the 1,000-year storm, make some edits, and then copy and do a couple smaller edits to minimize the amount of clicks. So I'll click Create here, and then let's go up to our Meteorologic Model Manager. Here's the 100-year model that we just created. What I want to do is a few things. First, change the precipitation type to not specified hydrograph, but rather hypothetical storm, which is this one here, and then click Save. And then in the Basins tab right here, I want to change Include Subbasins for the Tule River No Snow model. So just double click, change the no to a yes, and then that looks good. When I click Save here, I now have some new records pop up, some new icons appear in my Watershed Explorer. What I want to do is click on the hypothetical storm here and then make some edits to the components associated with this precipitation method. For method, I'm going to select User Specified Pattern. And then once you make that selection, the parameters down below change, some of them. The storm pattern is going to be CA Region 10 24-hour quarter 1 at 10% right here. The storm duration is going to be 24 hours. And then precipitation method will be Precipitation-Frequency grid. After that, the grid we want to select is the 814 100-year. This is the 1,000-year grid. The computation point will always just be the basin. Reservoir inflow is the name of the element. It's the junction right down here. For area reduction, we want to set user specified. And then the area reduction function is going to be our only one to choose from. That's the one that we just imported. Lastly, the spatial distribution will be variable by subbasin. I'm going to save that first, and then I'm going to make a couple copies. I think I can just right click, create a copy. Yeah, I can also do that in the meteorological model manager, but let's just create a copy this way. Then I'm going to paste in the 5,000 and then create one more copy. And this will be for the 10,000 year. Okay, so we have 1,000, that's good to go. And now we just created 5,000 and 10,000. The only change we need to make to the 5,000 and 10,000 is to update the grid with the appropriate grid for that return period. So for 5,000 year, I'm going to select the hypothetical storm icon, come down here to the components editor, change the grid to 5,000 years, and then hit save. For 10,000 years, I'm going to click the hypothetical storm and then for the grid, select 10,000 year and hit save. We're on to step 6, and that means it's time to create a control specification. So click new and give it a name, create. I'm going to close that window and then go ahead and define the actual start and end date time for that controlled specification we just created. 24-hour hypo. This is going to be for the first 2 days of the year 2100. So really thinking ahead here. January 1st here at midnight for the next 24 hours, or 48 hours, excuse me, through January 2nd. And that will be on a 15-minute time interval. The next step we're on is step 7. This is where we want to create and run the simulation runs. So to create them, we'll go up to the compute menu and we can go create compute simulation run, or another way to do it is compute and then simulation run manager. So we can see which runs we have already and then click new if we want to create a new one. This first one I'm going to select, I'm just going to name it 1,000 year for 24 hour. We're going to do the same thing as we did with MET models. We're going to create 3 separate simulation runs, each with their own MET model for the 1,000, 5,000, and 10,000. Okay, so for the basin model, we'll select Tule River, no snow. And the next, for the MET model, this will be 1,000 year, which is right there. Next. And then each time we're going to use that 48-hour hypo for our control specification. Finish, and that looks good. I could be making copies in the simulation run manager by selecting that record, copy, and so on, but I'm going to do that from the Watershed Explorer. I'm going to select the compute tab, and here I'm going to expand the simulation runs directory. Here's the simulation run we just created. I'm going to go ahead and make a copy from here, right click, create a copy, and then this will be the 5,000 year, and create a copy again. And this will be the 10,000 year. So for these 2 new simulation runs, I want to update the meteorologic model. I'm clicking on the 5,000 year simulation run, and then down here in the components editor, I'm going to select 5,000 and save. Also for 10,000, the meteorologic model will be 10,000 year and save. All right, we're ready to run the actual models, and let's go up to compute and then compute multiple. I'm going to put a checkbox by the 3 simulation runs and then compute and then wait for those to run. So there's the first one, the second one, and the third one. All right, looks good. I'll go ahead and close those records. Just out of curiosity, I want to just kind of briefly look at the hydrograph at the outlet of the watershed first, and then I'm going to actually record the actual data for the peak flow. So let's see, right now, let's select 1,000 year, and I'm just kind of curious about what the peak flow is. So right click and view the graph of that hydrograph. Here we have a peak flow of 73,000. That's cool. So that's huge. But with 5,000, we should expect even higher number. So let's see what that looks like. Here is that hydrograph. It is 250,000 almost. Okay. Is that right? No, that's not right. Okay, that was not right. I just noticed that I selected the wrong grid for 5,000. If you were watching along and you saw me make that mistake earlier on, then kudos to you there. We're going to go ahead and run that one more time. So 5,000, running the 5,000 model because the result was a little bit higher than I expected. It should be around 213,000 CFS. So let's take a peek there, graph. Okay, so that's closer to what I expected, about 210, 212. And then now let's select that 10,000 year number and then right click graph. Oh, I'm sorry, that's 1,000 again. I'm sorry, that looked like the 1,000 results, but I have 10,000 selected here. Let me check the MET model one more time. Sorry, being a little sloppy here. So 10,000 year, expand that. Yeah, this needs to be 10,000 and then save. Okay, let's try that again. So 10,000, run the simulation, and this should be around 250, 249,000. And graph. Yes, okay, that's what I expected to see. Let's get the actual numbers. So I'm going to just click on the results tab. This is probably one of the quicker ways to do it. For 1,000 year, I'm going to select global summary. And this is one of many ways to find the peak flow. 172,269 CFS for the 1,000 year peak flow, 24-hour storm right here at the outlet. Then if I collapse that, the 5,000 year, we said it was around 212 CFS. So if we click on that, that's 213,649.6 CFS. For 10,000 a year, we have 249,910 CFS. All right, next up, we're on to step 8, and the instructions tell us to compare to inflow frequency curves. So I'm going to bring up the instructions here. And what it has is a link to USGS. So you can go ahead and check that link out if you want, but basically it provides data for the 2-year up to the 500-year precipitation events. And if you scroll down a little bit, there's another link here. This is to an Excel file. We do want to download this file because the data from that USGS link was used to create the data in this Excel file. So I'm going to go ahead and single left click, and it looks like that downloaded already. All right, so I got it over here on my desktop. I'm going to open that up. And then here is that Excel file. There are 4 worksheets, sheet 1, and then 1,000 year, 5,000 year, and 10,000 year down here on the bottom. And what it has is it has some data that's used for a plot. So on this first sheet, sheet 1, if I scroll over to the right, I see a plot of data. So we have the 2-year up to the 500-year event with some uncertainty. Then what the instructions tell us to do is to paste in the values that we just calculated for the 1,000, 5,000, and 10,000 year peak flow into these 3 orange cells, which is G11 through 13. So let's go ahead and do that. I'm pasting in the 172,000 number for the 1,000 year event. And then there's the 5,000 year event. All right. So there's the 10,000 year event. Now, if I go back over to the plot here, what it did is it added these 3 data points here for 1,000, 5,000, and 10,000. It also goes on to mention that these events seem to run right along the imaginary line carried forward from the upper bound of the stream stats data from the USGS website that was used to create the peak discharge values up to the 500-year precipitation event. The tabs for 1,000 year, 5,000 year, and 10,000 year. And as you can see, there's not a whole lot right now. We will return to this at the very end of the exercise and paste data in here, which will populate these values, and then we'll also update our plot right here. All right, so just go ahead and minimize the Excel file for now. Next up is step 9, running an uncertainty analysis for temporal patterns and for the area reduction functions for the 1,000 year precipitation event. So first we're going to talk about the temporal uncertainty, and then after that, the area reduction function uncertainty. First, we're going to go up to the Tools menu, Data, Atlas 14, and then Parameter Value Sample Creator. So let me go ahead and do that. Tools, Data, Atlas 14, Parameter Value Sample Calculator. I'm going to select on Storm Pattern, and then here are our 36 storm patterns that we already loaded up. So I'm going to go ahead and just, on my keyboard, go Control A to just select all of them at once, and then click the arrow right button, and then click Next. Now what it's doing is it's asking me to give a name to the parameter value sample, and then I'm just going to call it A14 temporals, and then Next, and then yes, project DSS file, that works. So we'll click Next, and then process complete, what it tells me, so that looks good. I'll go ahead and click close. We will use the uncertainty analysis tool in HMS to see the effect the temporal pattern has on the peak flow response for this 1,000 year precipitation event. The next step is to go up to the compute menu, uncertainty analysis manager, and then I'm going to go and click new. I'm going to give this a name for 1,000 year temporal only, and then next. I'm going to select Tule River, no snow for the basin. And then for the meteorologic model will be 1,000 year 24-hour and finish. Okay, so we can close that. In the Watershed Explorer, go ahead and click on the Compute tab. I've already got that selected here. And now we have a directory for uncertainty analysis. I'll open that up and then select temporal only uncertainty analysis. Down here in the components editor, down here by analysis points, it just says selected, but I'm going to click this little gear icon here to the right. And then what I want to select is the reservoir inflow row here, and then check that checkbox. It actually serves as a junction. It's the time series outflow for 1 hour interval. So click save and then click close. Further down, we want to specify the start and end date time for the simulation. So that's going to be January 1 at in the year 2100. And then the end is going to be 2 days later at January 3. So it's going to be a 48-hour simulation. And then the time interval will be 15 minutes. These are just values coming from the instructions. And then after that, the number of samples is going to be 36 because we have 36 different temporal storm patterns. And then lastly, the instructions tell us to leave this seed value as it is. So I'm going to go ahead and click save. And next we're ready to add a parameter. So I'm going to go right click, add parameter, and then click on parameter 1 to define the parameter data. I'm going to select precipitation parameters here. And then for the parameter value name here, it's going to be hypothetical storm pattern. And then the method here will be sequential loop. So I want to keep it just as it is. And then the parameter value is going to be A14 temporals. This is the only choice. All right, so we'll go ahead and click save to that. Now we're ready to run our uncertainty analysis. So go ahead and select on that 1000 year temporal only uncertainty analysis. We can do the same thing up here in the compute toolbar and then go ahead and click compute and then let that run. We should have 36 different realizations, they're called here, for the different storm patterns. Okay, so it's finishing up here and it looks like it's completed. So that looks good. I'll click close here. Now in the Watershed Explorer, I'm going to click on the Results tab and then expand my uncertainty analysis and then select on a run. Now for this icon that reads Reservoir Inflow, I'm going to select that and then click on this Outflow graph. And what it shows me is basically a mean, min, max, and then mean plus and minus standard deviation curves of a hydrograph, which is the flow in CFS versus the 2-day simulation window. So for instance, the mean here is in solid blue, and it shows a peak of around maybe 70,000 CFS. And then our maximum is right up here. It shows a maximum of over maybe 260, 265 CFS. And remember, this is for the 1,000 year precipitation event, not the 10,000 year. We do see 172, which is similar to the data that we originally came up with in our previous trial when we ran the simulation run by itself for 1,000 year. So I think that's might be what that is right there. We have a minimum curve, and then we also have a mean minus standard deviation and a mean plus standard deviation. There seems to be a lot of variability in this temporal uncertainty analysis. If we want to look at the data, we can go File and then Tabulate if we need that data for whatever reason, and then I'll click Close. We also have maximum outflow right here, and there should be 36 rows. Yeah, so we have 36 different simulations that ran or realizations for the different storm patterns. And here we have 172, so that looks familiar. It must have been the same seed number. Yeah, we can just see how that peak CFS, the peak flow in CFS measures up between the different storm patterns. The last one here, I believe, is the largest, which is the fourth quartile, 90%. And then also we have some data here for outflow volume. Now we weren't really keeping track of volume for this particular exercise, but it's just wanted to point it out that that data exists. Next, we want to analyze the area reduction uncertainty. Previously, we assumed this dam or reservoir that's located in California uses the Sierra region for its area reduction function, but it could also be assumed to be located in the Central Valley region. So we're going to add two different area reduction function curves and check out the analysis and how it compares using the Sierra area reduction functions that we already used the first time. What I'm talking about here is if I go up to the Watershed Explorer and then click on Meteorologic Models to expand that, I'll click on 1000 year. And then if I click on hypothetical storm icon, I now have my area reduction function right here, HMR 59, Sierra, and 24 hour. So we only have one curve that we used the first time. The tutorial page then proceeds to show a couple different maps of California. showing the storm locations, and then another map for regional boundaries of the depth area duration relationships. So what we're going to do is create two more area reduction functions in the components menu. So I'll go up to components, paired data manager, and then the type is going to be area reduction functions. So we should already have one in there. There it is. Yeah, there's the one that I was talking about. So I'm going to go ahead and click new. We're going to create two new area reduction functions. There's the first one. This is CV is going to be short for Central Valley. Then I'll click new, and then this will be our third area reduction function. I'll just call it 1007, and then close that up. Next, I need to define that data. So I'm going to go to paired data, and then see area reduction functions here. I'll expand that. Now we need to put the data in for Central Valley. That's CV. We're just going to go with manual entry and then keep the units the same, miles squared and dimensionless. So I'll click on the table tab. I've already copied the data onto my clipboard. I'll go ahead and just paste it in. So we're using the same rows here for the area, but we're going to have different reduction factors than we use for all three will be slightly unique. So I'll go ahead and save that. Then 1007, the table, let me check the paired data tab. Yes, that looks correct. I'll click on the table tab and then paste in the data for the 1007 curve and hit save. I've created a plot that just shows the difference between these three different area reduction factors or functions, if you will. And what it is they all start at 1, of course, and they all decrease as the area increases. This is area in miles squared. So I didn't go out to the 10,000 point. I just went up to 5,000. So you can see there's a little bit of variation. The one that we already used is this Sierra 24-hour, which is in blue. So the two new ones are going to have a little bit more of a reduction as the area increases. That's the Central Valley and the 1007, two different storm functions. Next, we need to add parameter value samples in our paired data manager. So let's go up to components, paired data manager, and then for the type, we want to go all the way to the bottom. At least for me here, it's the last one, parameter value samples. Go ahead and click new. We're going to call this one ARF curves, and then create. And then we can close that up. Let's go ahead and define those curves. So it's this here, parameter value samples. This is the one we just created. Okay, down here in the components editor, we need to make some updates. The data source will be manual, that's fine. Category will be precipitation. And then the method is going to be hypothetical storm. And then the parameter is going to be area reduction functions. Click save. Now the table data, we need to enter the different area reduction functions by name here. So here's the first one. Okay, then here's the second one, that's Sierra. And then here's the last one, number 3. That's our storm event 1007. So just 3. I'll go ahead and click save there. Next, I'm going to go up to the Watershed Explorer and click on the Compute tab. Right here, we have our first uncertainty analysis record. We're going to make a copy of that now and go right-click, create a copy. Now for the name. And then for the name here, I'm going to just call it 1000 year ARF only. Click copy. All right, so this is the one we created. In the parameter, we need to make a few updates. So I'm going to go ahead and click on the parameter. The parameter here is going to be area reduction functions, which is here. And then the parameter value is going to be ARF curves. So go ahead and make those updates and then click save. Next, I'm going to go ahead and click the uncertainty analysis tab down here. Then what I need to do is change total samples from 36 down to 12. Now we only have 3 samples, but the instructions say that there's a minimum of 10. The smallest multiple of 3, that's at least 10 is 12. But I think 3 also works, but I'm just going to run it at 12 and see what happens. And then, yeah, we're ready to go. All the other data here that was copied over, like the start and end date time and so on, that's exactly what we want. Click save. And then we're in the compute tab. So I can just right click and compute. So we have 12 different realizations it should run through. Okay, that finished up. So I'll click close. Let's check out some of those results. So I'm going to go click on the results tab here and expand my uncertainty analysis for the 1000 year area reduction function. And then click on reservoir inflow. This is my junction representing the inflow of the reservoir. And let's click on that outflow tab. So here we have a plot. It's a hydrograph similar to what we saw last time in terms of the format and the style, but you can see we have far less variability as opposed to the previous plot, which was all over the place. All of the values seem to peak right here. Let me zoom in a little bit, and let me zoom in a little bit more. Very nice. So we have our mean value here, which seems to peak around 165. The peak value, the maximum is here. It seems to peak at about 172, and then the minimum would be around 155, 156. I should also be able to see the actual values for the maximum, which would be right here in this table for maximum outflow. And here are our 12 different realizations or samples. Now it does repeat because like 1 and 4 and 7 and 10 should all be the same, and it looks like they are. So I don't know if that's necessary to run 12. We can try that. But anyway, we basically range between 157,000 and 172,000 based on the variability of the three different area reduction functions. We can also look up the actual parameters themselves. So yeah, just repeating. So 1, 2, and 3. Let me just run that with 3 times and see if that works. So I'm going to change that 12 to a 3 and then save and then run. Okay. So I don't see any problem with that. Close. Let's look at the results now. And then right here, reservoir inflow. Okay, that looks correct. That looks fine. Yeah, so this is a little cleaner. We just need 3 records here. 157 up to 172. So the sample number here refers to the area reduction factor, which it would be nice if it was actually labeled, but that's no problem. We can just go to the parameter value here. So 1, 2, and 3 correspond to Central Valley, Sierra, and 1007. So let's go back to those maximum outflows. We have Central Valley at 157, and then Sierra was right here. That's the second one. And then the last one was 1007. The last part of the instructions here, and we're almost done, guys, is to run a combined analysis for uncertainty for both the temporal pattern uncertainty and area reduction at the same time. So to do that, I'm going to go to the Watershed Explorer, click on Compute, and now I'm going to make a copy of the temporal only record, which was the first one we did right here, and then copy. For the name, I'm going to say 1000-year temporal and area reduction functions and copy. So that came up right here. Now I need to create a second parameter. So this parameter 1 refers to the temporal only because that was what I made the copy from. So I need to make another parameter. So I'm going to go right click and then add parameter. For this parameter 2 here, down here in the components editor, let's go ahead and select the precipitation parameters. And then for the parameter here, I'm going to select area reduction function. For the method, this is going to be new. I'm going to change it to random independently random, which is this one right here, the last one. And then the value is just going to be the ARF curves, and then click save. What's really important is we need to go back to parameter 1 as well and change that to hypothetical storm pattern. That's correct. And then for the method, we also want to say random, independently random. And then the parameter value also needs to be updated when we change the method, but it's the same value. It's A14 temporals, and then save. The last thing we need to do before running this uncertainty analysis is to increase the number of trials. So before it was just 3, or I'm sorry, 36 or 12, whatever. We need to have 3 times 36, which is 108. The instructions tell us to just use 200. So I'm just going to go 200 down here for total samples and then click save. And then we should be ready to roll. So let's compute that uncertainty analysis. The instructions say it could take a couple minutes. So there's going to be 200 realizations. We've done 10 so far, so we're 5% done. All right, we're finishing up here. Looks like we're done there. I'll click close. So let's go ahead and check out those results. Okay, I'll click on the results tab here. And now for temporal and ARF, let's click on reservoir inflow and now click on that outflow graph. What we have is a graph that's similar to what we saw the first time with temporal only, which makes sense because there's a lot more variability there. The instructions actually tell us to click on the maximum outflow for the 200 trials. So what we have here is 200 different peak flows for the simulation going down to the bottom. So let's go ahead and just copy those values. I'm just scrolling down and dragging down to 200. Okay. On the keyboard, I'm going to go Control C. So hopefully this works. Now I'm going to bring up that Excel file with the plot that we had here earlier in the exercise. And then what I want to do here is here's the plot. And then if I scroll over, here's the data. We typed in our 3 numbers here earlier. What I want to do with that 200 records on my clipboard is come over here to the 1000 year tab. And then starting here at cell B2 is just right click and then paste. And then as you see, we have 2000 records, or sorry, 200 records of data. And then the min and max and some of the calculations over here in cell F or column F populated appropriately. And then what the instructions tell us to do is to go back to sheet 1 and then click on, scroll over to that plot. And what it did is it added a line to the plot here, I think. Okay, it might be kind of hard to see, but there is a vertical line here that represents the 5% and 95% quartile values, which are 71 and 189, and that's 1000 CFS. And that's it. That's it for step number 9. Step 10 tells us to do the same thing that we did in step 9, but for the 5,000 year precipitation event and the 10,000 year precipitation event. And I'm just not going to do that. This exercise is long enough, but by all means, go ahead and follow the steps and do that, and then finally update that Excel file to view the plot. The instructions mention that we usually assume that a single temporal pattern and single area reduction function when running frequency events, and that leads us to underestimate the uncertainty of these two different factors. Real world storm events can exhibit incredible variability in spatial and temporal behavior, which we mostly represent with just a single representative area reduction function and temporal pattern.